something to make make our cities a little bit more sustainable, that could be a big deal globally. Sorry, I got a few messages here on Zoom that distracted me. Now, what can we do today? Well, the interesting condition today is what you see here, the convergence of digital and physical. And, you know, it's, another way to say it is the internet becoming Internet of Things that's changing the way we can collect data from cities. In particular, today, I'll show some examples of how we can collect data from infrastructure, and then we can use the data, analyze the data to better understand what's going on, and then use it to make better decisions on how we transform the built environment. And we're doing that primarily with Senseable City Lab, our research lab at MIT. Again, main lab in Cambridge, Massachusetts, but MIT also has a research operation in Singapore. So we got a few people there using Singapore as a test bed. But also when it becomes design, or, you know, when with our design office, or with the startups that are coming out of both the MIT lab and the office. Now, I want to start with looking at mobility and a few examples. First of all, today we can look at a city like this. You know, we couldn't a few years ago. That's actually Lisbon, mapped using billions of data points collected from the mobility network. But we can get this information today, again, look at the city like a living organism. And then when we got the data, we can analyze it and discover interesting things. That's a similar type of data that we saw before in Lisbon. That's New York. This is actually JFK Airport. Every dot is a taxi pickup or drop off. Yellow is a pickup, blue is a drop off. You see JFK, as you zoom out, you see actually JFK was down there in the south. You see Manhattan and all of the boroughs. And incidentally, this is data that was made accessible by the Taxi and Limousine Commission for research. So again, open data that helped, you know, a number, you know, many papers came out of analyzing this, including some of the work that we started doing. And the first question we ask ourselves is, you know, well, you know, how many trips are potentially shareable in New York? If you look at those 2 points, between those 2 points in the course of a year, you got hundreds of thousands of trips. And, you know, the question is, you know, imagine you want to get a small delay in arrival, a small delta time of 1, 2, or 3 minutes, so very limited. How many trips could be combined? 2 people taking the same taxi. Now, in order to answer that question, we had to develop a different approach. If you look at traditional approaches, such as linear programming, they fail when you get so much data. So we developed something we call shareability networks. You see here these kind of networks that actually densify. Here, figure D and D, you see the network densifies if you tolerate a longer delay in arrival. So you got more possible combinations you can have, and then you analyze it, and when you can find an optimal solution. And the interesting thing is that, as you see there at the top, in Manhattan, you could take everybody to destination when they need to be there with a small delay, you know, you're talking about 100 to 100 seconds, but with 40% cars than what we have today. Now, the interesting thing, by the way, is that when the first results came out, they came to Uber noticed them, and then they reached out. We started a collaboration between a research collaboration between MIT and Uber. And as you might know, now Uber Pool at the time didn't exist, but Uber Pool today does exactly this: allow 2 people going more or less in the same direction to share a ride. You know, and that's Uber Pool, but also many other companies such as Via or Lyft or Didi in China and so on have developed similar things, which means, you know, two trips become one, so 1 less car on the road, which is less congestion, less consumption, and less pollution potentially. All other things being equal, that's very important in our cities. Now, we've been working on the same data set also more recently. This is a paper from a year and a half ago. And here we've been asking ourselves a different question, which is, you know, what is the minimum fleet we need in order to keep Manhattan on the move? You see here a little video. So here again is the same data we saw before. You can imagine that tomorrow a lot of this is self-driving cars. You know, self-driving cars are just, you know, behave in a very similar way to taxi. They are shared, they give a lift to someone and somebody else. And then if you look at what happens today, you see that dispatching is very inefficient. And so just by reprogramming the city, so again, how can we reduce the number of taxis in Manhattan? By reprogramming the way we do dispatching, and we called it the minimum fleet problem. So what is the minimum fleet we need? we can actually again have significant savings. And here you can see to the left and to the right of the image in a moment, you see the existing conditions, so the condition today with a lot of inefficiencies, and the condition we can have tomorrow. No sharing between trips, just reprogramming the way we assign people to vehicles. What will be more and more important, again, with self-driving cars. And if you look at self-driving cars, we could run the city with more intelligence. We're around 50% of the fleets we have today. Again, all other things being equal. So that's, well, that was a year and a half ago. I mean, I'm putting just a screenshot of the papers. If anybody's interested, you find all the papers on our website. Or at least the link to the paper. Now, so far we looked at, how we can look at the car as a piece of, as a probe that gives us information about where it is at what time. So we're talking about, X, Y, and time, where it is, lat long, and time. But the car itself collects a lot of data. So this is actually part of a project with a big car manufacturer. And you see here, an average car today has 2,000 to 3,000 signals. That means it collects data about, when you enter the car, if you got your hands on the steering wheel, but also, if it's raining. There are sensors, the one that turn on and off automatically the wipers, or the temperature outside, the temperature inside. You got information about how slippery the asphalt is. So the car is really like a sensor on wheels. And so we started looking at the car as an ambient sensing platform, but in particular, and I will not tell you much about this this paper, but in particular about how we can use the car in order to better understand infrastructure such as bridges and roads and so on. And in particular, if you look at bridges, I want to tell you a little story that's about Longfellow Bridge. I think many of you probably know it. That's a bridge that connects Cambridge and Boston downtown. And when Longfellow Bridge was being used regularly until when some serious structural investigations were carried out a few years ago, it was realized that the bridge was in a very dire situation. It had to be basically rebuilt at a cost of a few $100 million. You see it here being rebuilt. And also, the cost was also segregating, cutting the city in two, because, for a number of years, for 3 or 4 years until 2 years ago, you could only go from Cambridge to Boston, but not from Boston to Cambridge on the bridge. And the reason for that is that, bridge inspections are infrequent, subjective, and low-tech, as you see here, and they're expensive. If you put sensors such as this one that you see on the Golden Gate, to instrument fully a bridge, and again, you put sensors like this, you take fiber to collect the data, and you analyze the data, and then you send people for inspections. But to do that can set you off around $500,000 per year. And Crete wouldn't be able to do this for every bridge in the United States. But you know what, when you're doing this, what you're doing, you're just measuring frequencies. Usually you're measuring, call it the structural fingerprint of the bridge, basically focusing on the main frequencies of the bridge, and you constantly monitor them. You see if something changes, if there's changes, modal changes, in order to understand if if the bridge is having, if there's kind of structural damage that has happened. But today, as we got accelerometers everywhere. As I mentioned, accelerometers and gyroscopes are part of the 3,000 sensors into the car I mentioned before. They're pretty precise, but also we got very good accelerometers and gyroscopes in our phones, or we can buy in a very inexpensive way, like you see there, the little orange box, some professional accelerometer and gyroscopes. So we said, what if we could actually use this data in order to monitor the status of the infrastructure? And, we started collecting data on the Golden Gate Bridge for a very simple reason. The Golden Gate has been studied so much that we got a perfect ground truth. So the data we can collect is very easily comparable with the ground truth, with all the data has been collected for decades from the bridge. So we started doing this. We started going across the bridge. That's our team of researchers and students going across the Golden Gate over 100 times. I think, after 100 times, the San Francisco police got a bit suspicious, so they were pulled over, and they had to stop collecting data. But anyway, we got the data that you see here. The data you see here is time and frequencies collected from the different sensors I showed before, primarily the phones and the other orange one, the professional accelerometer. And then we started trying to analyze this, and it turns out, and actually we got a paper there's a paper out on this, the one I showed before, in Transactions of the IEEE. There's a new one under review right now that goes more in detail. It turns out we can identify the main frequencies. And so again, this might be, probably will never be as accurate as really instrumenting a bridge with very expensive sensors, but it's a bit like when you go to hospital. First you go triage, you know, they measure your temperature, maybe your blood pressure, and then if needed, they send you to do an MRI. So again, we could have a very cheap, inexpensive way to monitor thousands of miles of infrastructure. And actually the exciting thing is that now we are beyond the Golden Gate, we are scaling up. And so we've been working with data from Uber, from different cities. Again, you know, somehow with one single app, you know, and with very little investment, you can monitor many cities or entire countries. So we're working with data from Uber in the United States, and also with Allianz, the German insurer, in order to scale up for an entire European country and look at all the highway system in the country and start to monitor it. Now, I was saying that the car has already 2,000, 3,000 sensors, but if you add 2 little sensors like the one you see there, the 2 little ears, and those are LiDAR sensors. And the LiDAR does a 3-dimensional scan of the city, a little bit like what you see here, and then you feed all of that and other information into an artificial intelligence system, and the car drives itself. You know, that's not the future, that's the present as we speak. There's thousands and thousands of cars being tested. We've been part of the large project launched by the city of Singapore. We actually helped to lead some of those initiatives with self-driving cars. We know that we are not yet self-driving at level 5 autonomy, but you know, progress is continuing, and somehow the car is becoming more and more autonomous. Well, when a car becomes autonomous, there's other consequences again for urban infrastructure. One clear consequence is about this. Today we know that the car is parked 95% of the time. So here we have a very expensive machine. It costs a lot of energy to produce, to maintain, a lot of money. And you know what? Not only 95% of the time we don't use it, but it uses valuable space in our cities. As you see here, you know, it's all the parking spaces we need. So in some recent papers, we started looking at you know, theoretically, again, call it a bit, again, the minimum number of parking, the equivalent of the minimum fleet paper you saw before, but what is the minimum number of parking places we might need if we move to autonomy? And we find actually a very interesting curve. Clearly, there's a trade-off, because if you got self-driving cars, you can keep them always on the move, and then you need 0 parking spaces. But that doesn't seem to be a very smart solution, because you need a lot of energy, a lot of fuel, a lot of electricity to keep them on the move. So again, you get a very interesting trade-off curve. But based on the trade-off, if you say that you want to keep the total number of miles traveled, the increase in total number of miles traveled very limited, say 10%, you can actually still have very significant gains in parking. Today, Singapore has 1.37 million parking spaces, and tomorrow you can go to 400,000 or even less. So you can have a reduction between 70 to 80%. Again, there's a couple of papers. This is the last one from a few months ago. We call the minimum parking problem with this kind of trade-off. There's a previous one. It depends a bit on the assumptions you make. I mean, on what you want to, how you want to manage the trade-off. What is the limit you want to put on the slight increase in travel mile? The curves are very interesting, and that you get. And so anyway, that is that again can help us to rethink cities and rethink and repurpose a huge chunk of urban infrastructure. Another type of urban infrastructure, you know, that we are all familiar with is what you see here. That's a very well-known traffic light. And traffic lights actually appeared on our roads when cars appear on our roads. But if you got an intelligent system where every car knows where it is and where all the other cars are, you need to stop anymore. You can keep on going, just avoiding collisions. A little bit like this. Don't try it yet, please. But you know, if you look at this, you know, you can get more efficient, more sophisticated system. By the way, this is not our visualization, but we have a couple of papers that look at this, that actually try to extend Q in theory in order to address mathematically this problem. And again, you can think about a piece of urban infrastructure and how it can be redesigned. Just a few other things. As I mentioned at the beginning, we're also trying to then work with our design office to take some of these ideas into the real world. This has been a project where we collaborated with Google's sister company, Sidewalk Lab. in Toronto. And you know, the question we had, can we redesign the street more dynamically when we got self-driving cars? And then the idea is, well, you can have a street where in the morning you use it for more lanes when you got rush hour, and then midday you could have kids playing, in the evening you could have a party. And again, this with a little robot that moves, reconfigures parts of the city. And actually that's still in Toronto, there's still in a garage space that was used by Sidewalk Lab, there's still a prototype of the system as you see it here being tested. And the same thing also in another project, again, a speculative project in the city of Paris. It was part of a larger competition called the Reinventing Paris, Reinventer Paris. And here again, this was looking at 2050. So how in 2050 the infrastructure that is provided by this big urban highway called the Peripheric could be made more flexible, as you see here, a bit like in Toronto, but also can become reconfigured dynamically. If you got self-driving, you can actually program cars. You don't need big barriers in the middle. You can actually reprogram lanes digitally instead of physically. Again, you can have a more secure system, a safer system, and again, then you can have more lanes during rush hour in the right direction you're going. Again, this is done today as well, but in an analog way. We're moving very heavy pieces of concrete, and we can start thinking about a more flexible way to reprogram, to use the city. Again, we are thinking about 2050, so still 25, 30 years ahead, how the city can become also the way to collect a lot of the energy we need for running, for moving the cars. This technology already exists. The only problem is that the megawatt hour produced like this today is still more expensive than if you install standard, photovoltaic cells. But again, if you manage to scale up and improve and decrease the cost, this would be a very interesting way, because somehow you got a lot of space that you already have, which is the road, that you don't need to go and cover entire parts of the country with new photovoltaic system. And also the idea that with self-driving and autonomy, with autonomy and electricity, so with AVs and DVs, we can also make highways safer, less polluted, and then we can also build closer to them. So again, that's more like a speculative image. I'm a structural engineer, so don't ask me how those beautiful glass terraces can stand. But the point is, how we can build closer to our infrastructure, because the infrastructure is going to become safer again and less polluting. Very briefly, a couple of other things. We've been working with the city of Amsterdam. They don't have a big road infrastructure. They have a lot of canals. And so they came to us, they wanted to experiment with self-driving cars. So we teamed up with CSAIL, Computer Science, Artificial Intelligence at MIT, with Daniela Roos. And we said, well, why do you want to do self-driving cars? Anyway, technology is developing, is progressing. There's many teams working on this, including our own team in Singapore. Why don't you focus on something else, on self-driving boats? We call them rowboats. And, with a robot, you can actually move people around or parcels around, as you see here, people around, as you see here. You can use it as a way to scan water quality, air quality, so as kind of moving probes in the city. But also you can use these as kind of floating pixels that you can reconfigure. So if you got an emergency or a big event, you can create a temporary bridge or a floating arena. So how this can become like a reconfigurable architecture for Amsterdam's canals. And actually that's nothing new. If you look at this, that's the beautiful city of Venice. And those are the gondolas that create a temporary bridge during a special day called the Festa del Redentore, once a year. But the beauty of technology is sometimes it helps us to do things we were doing in the past, just to do them better or in an easier way. Again, just some examples. These are, by the way, we got there's a lot of articles came out last week because somebody spotted some of our one-to-one floating self-driving boats, rowboats in the canals in Amsterdam. So I think that kind of went viral. So you can see them online. I will not show you that today. We show just first prototypes. You see, we had to see where to put the engines. We tried different configurations, as you see here, for the propellers, water jets like this. This was the first 1-to-4 scale prototype. The final one is more or less 13 feet long, 13 foot long. And you see here, here the first prototypes. You see how they move, you know, very controllable. You see here some other images. These were the first tests, and as I said, you know, now is 1-to-1. And you know, the interesting thing for this is that again, I will, if you want, we can comment later. I got more slides, but I will not show them now. But about the autonomy part, you know, the interesting thing is that here we can really get to autonomy level 5. And the reason is that, you know, that depends on two parameters, really, also for cars, on the complexity of the environment and on the speed. So even for cars, if you move at 15 kilometers an hour, 20 kilometers an hour, just to stay there, let alone to move it, but just to stay there in midair, it will cost you a lot of energy. And without taking into account the fact that it's enough that, you know, one of these might fall on somebody's head one day, and then, you know, the whole legislation is going to change, as it happened with helicopters in Manhattan. In Manhattan, one could, a few decades ago, take a helicopter from JFK to the MetLife building, and then after a very tragic accident, you know, that was banned, and today you cannot land in the middle of Manhattan anymore. So I don't think this will be a solution, you know, because let me tell you something else, that, you know, if you look at the helipads in Manhattan, I'm talking the solution for big cities or dense cities. If you think about the helipad in Manhattan, today they got a few tens of flights per hour taking off or landing, and everybody complains. But if you want to have a little impact on mobility in Manhattan, you saw before, you know, we would need probably not tens of flights an hour, but 10,000 or even 100,000 if you really wanted everybody to move with this. And so I personally don't think that would be the solution. I think drones can still be very interesting. That's a project we've been doing with a major railway operator, looking at drones that normally sit on the top of poles that get charged, and then they can be deployed when there's an accident, when you want to inspect, or when you need to monitor something on the highway itself. We can use drones for many other things, especially small drones, I think, for sensing, anyway, many applications, but I see this more like, you know, for smaller drones. The bigger drones, you know, kind of helicopters, will certainly play a role, but I think probably not in dense cities, more like, you know, outside in the countryside, you know, or in places where there's really no infrastructure. There's a very interesting project with drones in Africa, again, how they can become an alternative to existing road mobility, simply because, you know, it'd be too expensive to develop all of that infrastructure. And then finally, another little story. I mean, we talked about cars, about drones and so on, but we are a great fan of human powered mobility. This was the first project we did with e-bikes. It was around 10 years ago. It was called the Copenhagen wheel, a small bicycle wheels that you can mount on any bike and turn it into an e-bike. And actually, this was done by a company we then started as a startup. I think, you know, that's what we are all encouraged to do at MIT, to take the research we do and turn it into real world applications, and doing a startup is an easy way to do that. And super pedestrian, the company we started to produce the Copenhagen wheel, actually then work a lot on using sensors in order to do predictive analytics and predictive maintenance on the wheels. And so then has become one of the major operators in micromobility, well, one of the fastest growing operators in micromobility, because again, you know, micromobility, the problem with scooters and the fleets that you deploy in cities is really maintenance, how you manage the fleets. And by using all the sensors on the scooter, by using all the analytics, then, you know, an operation that normally is very onerous and, you know, makes most of the player you know, it makes them unprofitable, then allows you to turn upside down an entire industry. Now, this is what I want to share with you about infrastructure and some of our work about, you know, using data and sensing and dynamic sensing in order to better understand and maintain infrastructure. I had put together a few more slides, but I will stop here. Maybe you can start the conversation, which is more about offices and building occupancy. And that's more because, you know, certainly big change that will have a big impact on the infrastructure is what's going to happen following COVID. Are we going to go back to our offices? Are we going back to commuting or not? And we have some initial results from data from big data analytics on the MIT campus that shows that basically, if we move just to a virtual working environment, we are damaging our social networks. somehow weak ties, weak links in our social networks are starting to become even weaker, and that is could be an issue in the long term. So that's why we think that we will need to go back to offices, even if in a more flexible way. I got a few slides on that, but I would prefer to stop here and start, having a more interactive discussion.